This happens to be example 3 on page 215 in Larson. We have a rectangular page and it is to contain 24 square inches of print. The margins at the top and the bottom of the page are 1.5 inches and the margins on each side. So here is 1 inch and here is 1 inch, but here is 1.5 inches and down here is 1.5 inches. Margins on each side are 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So we want to look at the least amount of paper. This whole thing is the paper. So what I have here is that if I'm looking at this being x plus 1.5 plus 1.5, that's x plus 3 and y plus 2. That is my area. Alright, now this is the printed area. So we know the secondary equation that x times y has to equal 24. So now we have those two things. We have x's, we have y's. We're going to right away say that this is 24 over x. And we got to look at our domain. Our domain, we know that x has to be bigger than 0. Alright, so now we got to decide how big does it have to be. So we're looking at a minimum paper size, because of course if you are paying for paper you don't want to spend a lot of money. So what I'm going to do is I'm going to look at my area. It's x plus 3 times y plus 2. I'm going to substitute for my 24 over x plus 2. We could FOIL this out because it's easier to take derivatives of it, possibly. So when I multiply this out, I get 24 plus 2x plus 72 over x plus 6. That's my area. Now I'm looking at probably adding like terms, which is 30 plus 2x plus 72 over x. And let's see if we can take the area. We want to minimize the area. Derivative of a constant is 0, so we get 2 plus, and if I take the derivative of this, it's 72 over x. That's the same thing as 72x to the negative 1. So what I have here is negative 72 over x squared. And I set that equal to 0. So now I'm going to put this over to the other side. 2x squared equals 72. X squared equals 36, and x equals 6. Now I'm not going to put the negative because you can't have a negative length. So that's what I'm looking at is 6. And if I put a negative in, we wanted x being greater than. So let's see if we can do the first derivative test. I've got an endpoint at 0 and I've got it going bigger than that. So what I'm going to do is I'm going to do a first derivative test, and let's see if we can take in this number and let's see if we can put a 5. So if I put a 5 in here, I'm going to get 2 plus negative 72 over 25. Well, that's bigger than 2, so I'm going to have a negative number here. If I put in 6, I'm going to have 0. If I put in 7, I'm going to have 72 divided by 49, and I end up having a positive number here. This is what we call the sign chart of A prime. Now what I could do is actually make a table, and I'm going to put in 5, 6, and let's say 7. And what we end up with here is negative numbers, here's 0, and here's positive. If that's the case, what I have is I have a negative, a 0, and a positive, which means this is a minimum. Okay, using the first derivative test. So it looks like I have a minimum. Now what I want to do is see what my y value is going to be. So remember, y equals 24 over 6, so y equals 4. Alright, if that's the case, my page is going to have to be 6 plus 3 by 4 plus 2. So I'm looking at a 9 by 6 for my page, and that is in inches. That will allow us to use the smallest amount of paper. All right, here's example 5. Again, it's in Larson, page 217. 4 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle so that I make a maximum total area? Well, let's see. The area is going to be the square plus the circle. And they tell us that we only have 4 feet of wire. So basically we're looking at the perimeter of 4x plus 2 pi r, and that equals 4 feet. Now, I've got x's and I've got r's, and I got to look to see how big this is supposed to be. I don't know where my volume needs to be. So let's see, 4 feet of wire. If I do 4 feet divided by 4, that gives me 1. We could see if it's between 0 and 1. If we have any more than that, it might be, because if we had anything that was more than that, you'd end up with more than 4 feet. So x plus x plus x plus x equals 4. You get 4x equals 4, x equals 1. If I put x any bigger than that, then it's going to be bigger than 4 feet. So that's why my domain goes through there. So now I have an area, x squared plus pi r squared, and I need to solve for r. So I'm going to take this one over here, and I'm going to say 2 pi r equals 4 minus 4x, and r is going to be 4 minus 4x divided by 2 pi. R is 4, 1 minus x over 2 pi actually gives me a 2, so r equals 2 times 1 minus x over pi. There's my r value, and I'm going to plug it into here. So area is going to be x squared plus pi times 2 1 minus x over pi, and I'm going to square it. So I got to do a bunch of simplifying before I even take any derivatives. Area equals x squared plus, and what I'm going to have is this squares, so I'm going to have 2, 4, 1 minus x squared over pi. Remember, you square everything, so 2 squared, and this would be pi squared, which cancels out one of those. Here's our area. Now, it may be easier for us to expand it, so now we have x squared plus, and I'm going to take 4 over pi, and I'm going to go 1 minus 2x plus x squared. And now we can do some more simplifying, unless you like to do quotient rules. That is completely up to you. So now what we have here is we have 4 over pi minus 8x over pi plus 4x squared over pi. Now remember, pi is a constant. So let's take this derivative and see what we get. And I'm going to say the derivative is 2x plus, there's 0, minus 8 over pi, and that is x, plus 8 over pi times x equals 0. Well, let's see if we can pull out some pi's. I'm not quite sure if we can. There's no pi here, but let's try this. 1 over pi, and I could actually leave this as a 2 pi x, and I could leave this as a minus 8 over here, and this would be a plus 8x over here. The only thing that's going to be 0 is when I make this a 0. So I need to add those two together. And when I add those two together, I'm going to have 2 pi plus 8 minus 8, 1 over pi. So I've got to find out what's going to make that equal to 0. This will never be 0. This is a constant. So I take 2 pi plus 8, set it equal to 8, and x is going to be 8 over 2 pi plus 8. And I could reduce that to 4 over pi plus 4. So there is my x value. That is a ugly number, which is about 0.56. So here's my x value. That's my critical value, and I want to find a maximum area. So let's take x. Let's take a prime. We've got 0, we've got 0.56, and we've got 1. And what we're going to do is plug it into, not the derivative, into the original. And when I plug it into the original, 0 for x is just going to get me pi r squared. And pi r squared, remember we said that r is this? So if I stuck in 0, then I'm going to have 2 over pi. So pi r squared, pi over 2 pi squared, and I end up with about 12.73. That's my x. If I plug in 0.56, I get 0.56, and if I plug in 1, I get 1. This ends up being my maximum. That tells me that if I want a maximum area, I don't want to make a square at all. I want it all to go into the circle. So all the area, or all the wire, all the wire is used for the circle. No square. That'll give us the maximum. Okay? Alright, and I can't forget this one, and I did, so I'm going to stick it in there. So now, when I take 1684x squared minus 144x squared minus 900x squared, I get 640x squared plus 8640x minus 129600, and that equals 0. Now we have a quadratic. And what you can do is go right to the quadratic formula, or you can keep factoring out. 320 goes into both of these, and you end up with 2x squared plus 27x minus 405. And now we can factor this one. And the way we're going to factor it is we get x and 2x, and call this 45, this minus 9. Because the factoring is quite complex, what I would do is just use the quadratic formula. 320 never equals 0. You get x equals 9, and you get x equals a negative 22.5. I would have put this right in the quadratic formula and got these two numbers. We can't have a negative x, so we're not going to even look at that. Back over here, we have two values now. We're going to look at our domain. Okay? The most that this wire could be, it says that we have, let's see, 2 posts, 12 feet high. All right, 30 feet apart. So if I think about it, that's the smallest it could be. So I'm going to go from 0 to 30, because that is what x can be. It can go from 0 to 30. That's how far apart we are. So now we're going to take the x value, we're going to take the w value, we're going to put in 0, our critical number, and our endpoints. It's very important that we do that. When we plug this into the original equation, we're going to get 53.04, and we're going to get 50, and we're going to get 60.31. And we want the minimum amount. Well, here's my minimum. So the wires should be 9 feet from the base of the 12-foot pole.